Hello and welcome back to Aerospace and Mechanical Engineering Lab. Today we will discuss the strain gauge lab. We will talk about the theory behind the stress and strain, what they are. We will talk about the stress-strain curve and the relationship between a stress and a strain. We will move on to the methods we have to measure a stress and a strain. Essentially, what this means is that we are going to talk about strain gauges and load cells. And we will move on to talking about the lab itself and how to do the analysis for the lab, for this lab. Okay. What is a strain? A strain is simply defined as force per unit area, which essentially means that when you want to calculate it, you have to have some sort of a measurement of the load that you are applying at a beam or a rod or whatever, and divided it by the cross-sectional area. So it's very important to know that if this is the direction of the force, to find the stress in the same direction, you have to find the area, cross-sectional area that this load is being exerted on, and then divide the load or the force by the area. A positive stress sign essentially just means a tensile stress, and a negative one means a compressive stress. So it's just the direction thing, right? And a strain is defined as the deformation per unit length. So essentially means that you have to have a reference length. We usually use the initial length for the reference length. And you have to find the elongation after you apply a load, then divide the elongation by the initial length. You're going to have your strain. You have to keep in mind that the strain is unitless because we are dividing a unit of length by another unit of length, which makes a strain a dimensionless variable. A stress, on the other hand, is newtons per square meters. A positive sign for a strain means extension. A negative sign for a strain means compression. This is consistent with the stress. Negative sign compression, positive sign extension or tensile stress. Okay, so these two, a stress and a strain, are related to each other, and we can plot the stress-strain curve like this. You can see the stress-strain curve has a linear region, very small linear region, and a huge non-linear region. And this is where your material breaks, the rupture happens, essentially something like this. If you start, this is an example of a tensile test. We are applying force, a tensile force to this sample, and at some point, after some point, it will break. This breakage happens here. And throughout the process, we can measure the strain. Of course, we can calculate the strain, and we can measure the stress. If you graph it, they are going to have this sort of relationship. We are focused on this region, the linear region, which is called the elastic region. Essentially what it means that if you remove the stress during the elastic region, it will go back to its original form, whatever the original form was that your sample with. The relationship between the two in this region is a linear relationship, and we can use the Hooke's law to relate a stress to a strain. A stress is going to be related to a strain through modulus of elasticity, which is essentially based on Hooke's law. It is going to be our spring constant. So a stress is going to be equal to modulus of elasticity multiplied by the strain. This only applies to the elastic region. A modulus of elasticity is essentially the ability of the material to stay in the elastic region. Higher modulus of moduli of elasticity means that bigger elastic region. It is going to take longer for your material to yield. Okay, so we know the relationship between the two, but what we want to do and what we want to know is that how can we actually measure the stress and strain to find the modulus of elasticity for a material. Modulus of elasticity is a material property, and we are very interested in this property because it will help us design whatever we need to design, right? So how can we calculate this modulus of elasticity? Meaning that how can we do any measurements, do any stress and strain measurements? All of these measurements are done through sensors. In your bending and torsion lab, you have already used 2 digital sensors. We have measured the angle change during torsion, and we have also measured deflection through 3-point bending. But we want to learn how to actually connect the sensor to a computer so the computer can translate and read the data for us instead of us manually recording it. So electronic sensors are essentially going to receive an input. For our case, is that input a strain, is the strain or the stress, and then which are given to the sensor through an electric signal, and that electric signal is translated in the computer to convert it in the computer to a stress and or a strain. Okay. This a specific device that we are going to use for a strain gauge, a strain measurement, is called the strain gauge, which is essentially just an electrical circuit that is parallel in the direction of parallel to the direction of a strain, to the direction of the elongation. You usually install it so that is parallel to the direction of elongation, and then as your beam elongates, these wires are going to get closer to each other or further away, move further away from each other, which is going to change the resistance of this electrical system and eventually change the potential, electric potential or electric current that your computer is reading. And based on that change in the resistance of the circuit, you are going to see a strain. Like we have a relationship that relates a strain to the electrical resistance of your circuitry. Okay. This is another view of a strain gauge. As you can see, it has a metallic part, which is our electrical circuit, and these are the 2 terminals that are going to connect to your data acquisition device. Strain gauges are widely used everywhere, in the industry, in the academia, aerospace industry, car manufacturing. A lot of different locations are going to use strain gauges because these are very, very robust devices that are going to help us measure the strain at any point with a good deal of accuracy. Okay, but the relationship between resistance and the length of your beam is given using this equation, which essentially means that as long as you are keeping the material resistivity constant and the cross-sectional area does not change that much, the changes in the resistance can be related to elongation of the beam directly, and that elongation can be converted to a strain, the value we can actually use in our analysis. Okay, so in the lab, what's going to happen is you will be given a beam like this. This beam is going to have a strain gauge pre-installed at the location that is close to your fixed support, and we are going to have a load cell installed closer to the free end of the beam, our beam here. And then we have a dial that is going to help us create a load and at the free end of the beam, and that load is going to create that moment. It's going to create a moment here. That moment is going to cause a strain. We can relate the stress at this location to the moment or the force that is being exerted here through this equation. So stress at this location is going to be equal to your moment, which is your load, multiplied by this length, multiplied by y, and y is the distance between the location you are measuring the strain or you're applying the load on, the distance between this location and the neutral axis. Neutral axis for our beam is going to be the middle of the beam, middle of the thickness. So this y for us is going to be thickness of the beam divided by 2. So the first thing you want to measure is this arm, this moment arm first of all, and the thickness of the beam to be used in these equations. So we have the moment, we are reading the load, force, your load multiplied by this distance is going to give us the moment. We have the distance from the neutral axis, y, divided by the moment of inertia of the beam. This is a rectangular beam, so you know how to calculate the moment of inertia for a rectangle, and that is going to be equal to the stress at this specific point. Based on the Hooke's law, we can relate the stress to a strain through modulus of elasticity, which essentially means that your equation that you are going to use is going to be equal to a strain. A strain is going to be equal to moment multiplied by the distance from the neutral zone divided by the modulus of elasticity multiplied by your moment of inertia. And so your job is to calculate the modulus of elasticity for this specific beam. You have to make a couple of measurements. You make sure to watch the lab video. You have to make a couple of measurements, and using those measurements, let's say you make 5 measurements. Using those measurements, you can calculate 5 different moduli of elasticity, and using those 5 different values, you can do a statistical analysis. We want you to have an uncertainty level or confidence level of 90% in your statistical analysis. Please keep in mind that you only have 5 data points. That means that you have to use a student t-test for your confidence interval analysis. And here in the notes, it says you have to use the two different methods. You don't really need to use the 2 different methods. You can just use the one I explained and do the analysis. I'll make sure that this part is removed from the lecture notes when I upload the lecture notes.